Hello friends, in this session we will discuss about the control chart for attributes. We have already discussed the control chart for variables, and attributes are those quality parameters which cannot be directly measured, and it is measured in terms of the attribute, that is this is defective or not defective, how many number of defects are there. So this cannot be directly measured in the continuous number like weight, width, thickness, etc. So this may be judged by the quality inspector that this is good or bad. For example, if you want to find the color intensity of the product, then this is up to mark or not. If it is not up to mark, this is defective. If it is up to mark, this is the good product. So on this basis, the missing part of the particular machines, this can be indicated in terms of the attributes. So there are two types of the attributes where measurement are not possible. For example, visually inspected items such as color, missing parts, scratches and damages. Then in that situation we use the control chart for attributes. And second situation where measurement is possible but are not made because of involvement of the cost and time, and we can consider the attribute charts in place of the variable chart. For example, if you want to measure a particle shaft, then we can use go no go gauge. So using this go no go gauge, we can judge that this external diameter is okay or not okay. If we use the slip gauge, then using this slip gauge we can say that this is okay or not okay. So on the basis of that we can use the attribute chart without measuring the dimension. So these are the two types of the attributes. Now here we will discuss about the two types of the attribute chart. One is the defective chart and another one is the defect chart. So defective, there is difference between the defective and defect. If a product has even a single defect, this is known as defective. If a product has single defect or more than one defect, this will be defective. So if we do the control chart for that product, then this is known as defective chart. If you use the control chart for the particular number of defects, then this is known as defect chart. For defect chart we use the C chart and U chart, count of defect chart and defect per unit chart. And here P chart is used for the defective chart. So how to use this P chart we can learn here. We can see here this formulation. We will discuss about this formulation considering a numerical example. So here we can see that if we plot the defective chart, then there will be defective. There is only two options: defective or not defective. Not defective. So if we indicate the defective in terms of P, then the not defective will be 1 minus P. Not defective will be 1 minus P. So probability is only P and Q. Only P and Q. Q is 1 minus P. Q is 1 minus P. So the standard deviation is taken in this distribution from the binomial distribution, because in the binomial distribution there is only two options. This is binary type. This is okay or not okay, good or not good. So here Q indicates the good product and P indicates the defective product. So this Q will be 1 minus P. This is the reason that if you use the sigma value in the binomial distribution, then this sigma value will be PQ by N. PQ by N. So here we can write that P into 1 minus P by N. So this type of the sigma is used in the P chart, and we can see here that the rest of the process will be same, as we have to find the fraction defective for all the different subgroups, and then average fraction defective, and then plus minus 3 under root P bar into 1 minus P bar divided by N. So this is the concept of the finding the control limits in the P chart. So how to use this concept we will discuss considering one numerical example. Now see here, this is the numerical example. Yes. Now inspection results for the electric bulbs produced by a company in a month of 25 working days are shown in table 2. In table 2. So these are the different subgroups. In each subgroup there are 500 items, and all these 500 items are inspected. So this is the number inspected. This is indicated by N. This is indicated by n. This is the number inspected. Find the control charts limit using the control charts for defective. If the word defective is mentioned, then definitely we should use P chart, not the C chart or U chart, because P chart is only chart which is used for the defective chart here. So this is the number of defective in the among these 500 product. This is indicated by NP. This is number defective, and this is 18. 18 means after inspection of 500 items in the first subgroup, the number of defectives are 18. Similarly, in second subgroup, after inspection of the 500 items, the number of defectives are 5. Then we have to find the fraction defective. What is the interpretation of the fraction defective? Fraction defective means defective per unit item. So here we divide this number defective divided by the number of items inspected. So this is 18 divided by 500, so this will be 0.036. You can see here this is 0.036. In the similar fashion, 5 divided by 500, this is 0.01. So we will have to find the value of P, and this P is known as fraction defective. This is known as fraction defective. So fraction defective P is equal to NP by N. So this formula is used to find the value of P, and after finding the P value for all the different subgroups, we find the average value of P. Average value of P, summation of P divided by G. Summation of P divided by G. So total subgroups are 25. So we can use this 25 and we can find the value of P bar. After finding the P bar, we have already shown that what type of formula we can use here. So this is the P bar, and P bar plus minus 3 into under root P bar 1 minus P bar by N, that is PQ by N, and this is the 3 sigma and this is the 3 sigma. So plus 3 sigma and minus 3 sigma, this will be used, and this is the upper control limit, this is the lower control limit. And then we should plot the value of P in this chart corresponding to the different subgroups. Then we can see that this is out of control and this is out of control. So two values are out of control, and in this case again we want to find the revised control limits and revised center line. So here this P bar new will be equal to summation of P minus summation of P discarded divided by G minus GD. Here out of 24, 2 are discarded, so we can use 22 only. So we can see here that there was 25 subgroups, not 24 in this case. So we can see here this is 23 and 2 subgroups are discarded, and this is new value of the P bar. This is new value of P bar, and they put this new value of P bar in the same formula. So this is revised upper control limit, this is revised lower control limit. In this case no constant is taken from any table, and this is very simple, we can use this. But in this case we have to think that if the subgroup size is variable, then what should we do? Before doing this variable subgroup size, we would like to discuss about the different types of the defective chart. This may be the percent defective chart or the number defective chart. In the case of the percent defective chart, it is indicated in terms of percent, 100 P0. So 100 multiplied by the upper control limits, which is calculated there. So we can use this as a control limits. And this center line, this is NP0, and here this is upper control limit, lower control limit in the case of the number defective charts. Now see the variable subgroup size. If the subgroup size is variable like this, then you can see that the control limits is calculated using this formula. So n is here variable, n is here variable. So if n is variable, then this part will be completely variable. So for variable, for each subgroup there will be the different sub control limits. So you can see that if you plot this will be this type of the control chart. But this is very difficult to calculate for every and each subgroup the separate control limits, if it is required to calculate the manually. If it is to be used on the Excel sheet, then this is very easy. But at that time there was no availability of the Excel sheet or the Microsoft, etc. So nowadays this becomes very easy, but it was invented when there was no such type of the software. Then how to minimize the variability of this subgroup size in the calculation? If you calculate the suppose average subgroup size like this and average, then we can plot this type of the control limits. But in this case, if the point lies here, if you use the average subgroup size, then as per the average subgroup size, this is out of control. But if we consider this subgroup, then this is under control. So this is the problem. Similarly, if we consider this point, then according to the average subgroup size, this point is under control. But if we consider this individual subgroup, then this is out of control. So there may be some problem, and then there may be the error in the measurement. Then in that situation, what should we do? Now this can be considered in the easiest way. Now see this numerical example. This is the variable subgroup size. This is the variable subgroup size. Now you can see this is not constant. Now we can find the value of np divided by n. We can find the p value for all the different subgroup size, and then we can find the summation of p and divided by g. Then in that case we can find the p bar. So the p bar, there is no problem. We can calculate the p bar here, and you can also calculate the value of p bar summation of np divided by summation of n. That means considering all the value, then we can find the value of p bar. But here, if you use the average n, then there will be straight line, but some points which is out of control using the n average, this may be under control in the individual subgroup, and some subgroup which is under control, this may be the out of control. So how to deal this type of the situation here? So for dealing this type of the situation, you can see here, this is shown here. This is out of control, this is out of control. Similarly, this is out of control, this is out of control. Now you can use the individual control limits, but this is very complex. But if you want to minimize this effect of the variation, then what should we do? In that situation, we can use the average subgroup size. That is this average subgroup size. This is the p bar, and this is the UCL considering the n average, and this is LCL considering the n average. Now you can see that the formula is given as UCL and LCL. This is equal to p bar plus 3 under root p bar 1 minus p bar by n. So if the value of n increases, this value, the complete this term value will decrease, and this UCL and LCL will move towards the center line. That means it will move closer to the center line if n individual is greater than n average. If n is decreasing, that means n is smaller than the n average, that means this value will be larger, and in that situation it will move in this direction here. This will be wider. So if ni is less than n average, now see that we will compare the ni, that means individual subgroup size, with n average. If there is substantial difference, then we will see that ni is greater than n average or less than n average. If it is greater than n average, then definitely the individual control limit will be inside the average control limits, Okay, if the point lies outside this average control limits, then it will be definitely out of control in this situation also. So there is no need to find the individual control limit. But if it lies inside the control limits, then we do not know this line will lie here or here. So in that situation, we will have to find the individual control limits. Similarly, just opposite, if suppose ni is less than greater than n average, then this will lie inside, and if ni is less than n average, then it will lie outside this and average control limit. Then in that situation, if a point lie inside this control limit, then definitely it will be inside to this control limit also, so no need to find the individual control limit. But if it lies outside this and average control limit, then in that situation we will have to find out the individual control limits, because we do not know this outside control limits will be from here or here or here, we do not know. So in that situation we will have to find this. So this can be summarized in the fourth situation. Now you can see here, when points that is subgroup fraction defective falls inside the limits, this is the UCL, this is the LCL, this is the P bar. Falls falls inside the subgroup, for example here, inside the limits, and subgroup size is smaller than the average subgroup size. That means Ni is smaller than an average. That means for this Ni it is smaller, the control limits will be wider. That means this may go from here, and this point is already under control to this line, and this control individual control limit will be wider, then definitely it will be under control, so no need to find the individual control limit. So subgroup size is smaller than the average subgroup size, the individual control limits will be wider than the for the average subgroup size, therefore individual control limits are not needed, the data will be under control. But in the opposite situation, if when a point falls inside the central limit control limit, and if its subgroup size is larger, Ni is greater than an average, then this will the individual control limit, this will be inside this control limits, and we do not know this will be upper part of this point or lower part of this point. If it is lower part this point, this will be out of control. If it is upper part of this point, then this will be under control. Then in this situation we will have to find the individual control limits. So here this is written that when a point or subgroup fraction defective falls inside the limits, and the subgroup size is larger than the average subgroup size, and the difference in the subgroup is substantial, the individual control limit will be smaller than for the average subgroup size. Therefore individual control limits are needed to check the data is either under control or out of control. Similarly, in the another case, if the point lies outside this control limit, suppose this is UCL, this is LCL, and this is P bar, and if point lies here, for example, or lies here, then when a subgroup falls outside the limits, and its subgroup size is smaller than the average subgroup size, Ni is smaller than the N average, then the subgroup then the control limits of Ni will be wider, because smaller. So in that case we do not know this individual control limit will be from here or here or here. Then in that case we will have to find the individual control limits, and this is written that, and the difference on the subgroup size is substantial, the individual control limit will be wider than the average subgroup size, but individual control limits are needed to check the data that is either under control or out of control. Now, if the Ni is greater than an average, then definitely no need to find the individual control limit, because for this will be closer to this, so this may be from here or here, but here this point lies outside the average control limits, and then definitely this will be outside for this line also, so this is out of control, no need to find the individual control limits. So this is about the P chart. Now control chart for defects. This is for the count of defect. That means in one unit of the product, this product is mentioned here, that is item number, or you can say the coding of the item. This may be A101 or something. This will be given as the item number, and in one item how many defects are there. So this is indicated by C. This is known as count of defect. This is known as count of defect. So in this case we use the count of defect chart, and we find the value of C bar, and this C bar is summation of C divided by G. How many products are there, how many products are there. So this is G, and we can use the UCL will be equal to simply C bar plus 3 under root C bar. Now here we do not use C bar by n, because here n equal to 1. In one we find the number of defects in one product only, so the number of products in each subgroup is 1, so there is no need to write n. So we can write C bar plus minus 3 under root C bar only, and in this way we can find the control limits, upper control limit or the lower control limit. Now we can see this numerical example here, and this is the revised. Revision is the same process. The outside going the points will be discarded, and new C0 bar will be considered, and the same formula is used here. Now see this numerical example. This is the unit number 1, 2, 3, 4, and there are total 25 units, and in each unit how many defects are there, this is given. This is known as C, and we can find the summation of C divided by G. This will be equal to C bar. So what is the value of C bar? You can see that this C bar is given as 5.64. After calculation there are 25 products, so we can find this, and we can plot this value of C on the chart of C chart. This is known as upper control limit, UCL, and this is LCL, and there are 3 points. These are the out of control, so we can discard these 3 points in the revised control limits. So you can see that these are discarded, and here the total number of the products are only 22 in place of 25. 3 are already discarded. After finding the new value of C bar, we can place in the UCL and NCL, we can find this revised control limit. So this is about the control limit defect chart for C chart. And then U chart. In the case of U chart, there are more than one products in one subgroup. For example, this is subgroup, and there are 100 products in each subgroup. Suppose 100 products, then what is the total count of defects among the 100, and we want to find the defect per unit, defects per unit. So in this case we will have to divide C by n, and this is indicated by U. This is indicated by U. So this is known as defects per unit, because there are more number of units in each subgroup. Then in this situation we have to find the value of U bar. This will be summation of U divided by G. But here in each subgroup more than one product, so we will have to find the control limits as U bar plus minus 3 under root U bar by n. Here n is more than 1, therefore we should place the value of n, and in this way we can find the upper control limit and lower control limit. And if any subgroup is out of control, then again we should discard, and you should find the new value of U bar 0 by discarding that summation of U minus summation of U discarded. We will plot the U value and G minus GD, and then we will use in the same formula in place of U bar 0, then we can find the revised control limits. You can see here, this is the trial control limits, and this is the revised control limits. And in this case you can see that one point is only out of control, so only one data is out of control. Here this one data is out of control, so in this situation we can discard this data in the revised control limit. This is the trial central line, this is the trial upper control limit, trial lower control limit, and after removal of that data, this is the revised U bar 0, then you can find the revised upper control limit and lower control limit. So this is a defect per unit chart, and this is also known as U chart. Now see the demerit classification. The demerits are classified into 3 categories. This is a critical defect, major defect, and minor defect. What is the difference between these type of the defects? There are the defects in a product which results in hazardous or unsafe use. This is known as critical defect. That means if this defect occurs and if you use that product, this may be very dangerous. So this type of the defect is known as critical defect. Major defect means these are the defects in the product which results in failure of the working or the performance. This may not be very much dangerous, but this will affect the performance, or this will degrade the performance. Then this is known as a major defect. And minor defect, this is not very much serious, and this is only considered for the aesthetic value or the appearance of the product. Then this is known as minor defects. And we can uh, plot the control chart for these demerits also. This is known as demerit charts. So here this is the center line, and in this case we give the weightage to the critical defect and the major defect and minor defect. And this is WC is the weightage given to the critical defect, and WMA weighted for the major defect, and WMI weighted for the minor defect. And this weightage may be in terms of 9 3 1. That means 9 is to 3 is to 1. This is the weightage provided to the major defect, critical defect, major defect, and the minor defects. Now here, after finding the d bar, we can find the value of sigma 0. This will be the weight square UO for the, this is major, this is minor, and divided by n, and this will be the upper control limit, this will be the lower control limit. So this is the way of finding the control chart for demerits also. Thank you. Now we have completed the control chart for attributes.